Okay. Now, I had totally forgotten that. Let me find this in the site real quick. I'd totally forgotten that I had said something about on the site about homework being due today. So, and if I take a look at those problems, that there's only one of those problems out of the three that I've even covered enough for y'all to do. So, yeah, because then all of a sudden you figure out the assignment. It's like, we have a homework too. So I think, I'm definitely down to headspace to grade anything. So, well, okay, that's probably never true all the time, but okay. So, because right now we're in the midst of finite differences, which I'm going to continue with today, and problems 2 and 3 involve a fair amount of MATLAB. Sorry. Okay, that's a sorry, not sorry, but still. I do try to empathize, and haven't got to that either, and might not until Wednesday. So, and this chapter, if all goes well, I may be able to finish it by Wednesday. So that means that because when I canceled that class and decided to slow down on other things, I had not adjusted the assignment schedule. So, yeah. So it's going to be a while, a couple weeks at least. So, chill about anything homework related for now. And it would be a good idea if you haven't already spent some time on the first problem that doesn't involve MATLAB or finite differences. Has anyone? I know you have.
So I was just looking at, because to use the Fourier transform the same method that we used before, you have to look at the inner product at first. You have to multiply by the conjugate and integrate.
Right.
But since there's an extra term, do you just like my question? Do you still just like the 2 DUT?
Well,
just integrate that, or like?
Okay. And yes, you think in terms of like, okay, actually evaluating the integral, that's probably not the best way to go, just because that's you're in danger of going down quite the rabbit hole there. But like, the thing to keep in mind is that the Fourier transform of a time derivative is the time derivative of a transform. The two operations go in either order. So like you're trying to take Fourier transform as PDE, and you get an equation involving u hat.
Right.
So wherever you see a time derivative, you're going to have a time derivative of u hat. So that whole term, that 2d ut, would go over to 2d, it'll still be there because it's a constant, times u hat t.
Okay.
Because when you're taking a Fourier transform of a PDE, what that gives you is an ODE in t, where the omega order frequency variable happens to be a parameter in it.
Because then, I need to look at it some more. Because then I'm concerned that I'm not going to know what is like what is F and what is G.
Well, like the initial conditions, or
well, before when we did like the inverse transform of product, like when we were doing a compilation of
Oh,
Changing
okay.
sign. Because that's what we're going to have to do, right?
Well, okay. Like, since you're not really given a specific initial condition, and so what you could do is, when you get your ODE for U hat, your initial values would come from the transforms of whatever initial data, like F hat and G hat, and then your solution would just be um, would just be the inverse transform of that. Now, okay, like. So the inverse transform. Okay, hold on. Okay, so since this is periodic boundary conditions. Okay. This is in Fourier series. So you solve your system of ODE, your one parameter family of ODEs to fill in that part of the expression. And things I'm not looking for you to really simplify this in any way. There isn't really anything you can do with that, especially not having something specific for F hat, G hat anyway. But, because really what's going to happen here is this expression would be equal to something times F hat of omega plus something times G hat of omega. So, and we don't really care about F hat and G hat because they could be anything. It's what's multiplying them that is significant, because you can multiply that with e to the I omega x, and the last part of the question, like just examining how the waves travel with frequency-dependent velocities while being damped with time. So, so this is going to be e to the ik, or not ik. Actually, I think I used k in the notes. I don't remember. So I want to keep my notation consistent. Come on. Okay, yeah, for Fourier series I use k. Whereas I use omega for the continuous transform. Yeah, so this whole expression is going to be e to the ik something times f hat of k plus e to the ik something g hat of k. Now, there's definitely going to be an x in here just because of that. And then whatever's in here is going to depend on the t is going to be a factor in it. And what's in here is the wave speed. in both cases. Now, in the case of an ordinary wave equation, what you get here is just a constant. You have waves traveling at constant speed. Like when I derive D'Alembert's solution to a wave equation, you have like f of x plus ct and f of x minus ct. That c, or plus or minus c, is what pops up in here. The point of this problem is that whatever you get here, you have to show that it actually depends on k. Since the problem's asking about frequency-dependent velocities. Now, what you get in here, though, actually would have a real part and imaginary part. Now, the real part, because you've already factored out an I here, the real part of this will give you speed. But if whatever imaginary part in here, so if you have plus or minus I, we multiply with that to give you a real exponent. So E to be anything that is real times t is something that affects the amplitude of these waves over time. Because then it becomes a scaling factor. And it says, while being damped with time. So what you're looking for is, do we have a negative exponent? So that's causing exponential decay of these waves. So if you get something positive, then you know you messed up because that's exponential growth. All right, so those are things to look for. Okay. Now, once you've done that, so maybe you might find it the easiest homework problem of the semester. There's problems 2 and 3, like I mentioned, they concern MATLAB, but the first part of it is something that could be done on paper, because what you're in number 2. I'm getting all this. Okay. Okay, so in number 2, you're given this. I'll write the first part of the problem. Poisson's equation and boundary conditions. U0 equals 0. And you're given f. So f of x is sine 5x times 5 prime squared minus cosine 5x phi double prime x. Okay. Oh, all right. Okay. And this problem, when you implement a finite difference method in MATLAB to solve this with this function, and you're supposed to examine the error. Now, what we like to have when examining error is, of course, to have the exact solution. And for many problems, we don't. So we have to examine the error in other ways, like solving in a small time step or whatever, and then comparing our solutions to that. So like it's the closest we can get to an exact solution. But this is not one of those problems. Here we actually can get the exact solution from this. So can you find u so that minus u double prime is equal to f? So this is something that looks kind of nasty, but actually it's something that can be figured out. Now, not really in the most systematic way, but you can try to imagine like you go one derivative at a time, because you're trying to find where a second derivative is equal to this. So if you try backtracking one derivative at a time, what would be an integral of this? And ultimately want a second integral, because you can see how if you took sine of 5x and you take the derivative, what do you get? You get cosine of 5x times 5 prime. That's taking one derivative. But here we have 5 prime squared. That's going to come from taking a second derivative. But there's also a product rule at play here. It might actually not be a bad idea to try certain things by trial and error, like to try taking a derivative or two and see if it gets you this, and if not, like to adjust it. So the solution does have a simple form, and I suppose I could be more humane and give it to you. But sometimes I want you to have the experience of trying to solve a problem like this when you don't really have a kind of a blueprint. So you have these snippets of like, okay, this it looks like something that could result by differentiating. So I will tell you that the solution does have a fairly simple form to it. Because a lot of times when you take derivatives, especially involve products or compositions, derivatives become more complicated, not less. So we have to have a pretty simple function to start with if we're going to differentiate it twice and get something of only two terms. Let's give it your best shot and we'll see what happens. Yeah.
So whenever it's just u equals 0 like that, it's automatically those boundary conditions? Because like on the paper it just says u equals 0.
But it says u equals 0, but then it says x in a set 0, 1.
Oh.
Yeah, so you have to look at that. Oh, I forgot to mention 5x is
9 pi x squared.
Yeah, okay. All right. Okay. All right, so have fun with that. All right. But then, yeah, after that, it's MATLAB from that point on. Okay. Now, last time when only half of you were here, and the other half hopefully either has watched the video or will watch it soon. I worked through an equation like this, like a Poisson's equation. Actually, it was literally this problem, and how we get a finite difference scheme for it. But I want to. So one thing I omitted last time, I want to go back and get is just the general approach for how we come up with differentiation rules. I mentioned a few specific kinds, like forward difference, backward difference, center difference, etc. But what's the general idea and how we come up with these things? And also more general second-order linear equations. maybe by Wednesday can get to error analysis. Okay. I was up till 2 a.m. struggling with, guess what, something in MATLAB, so I'm not sure how well my brain is going to work, so I'm just going to make that disclaimer. And then I have to do that again tonight, so if I'm just full of nothing tomorrow, then you'll know. Okay. Yeah, late classes suck. I know. All right. So what I'm going to show you is, so if you're given values of a function that you want to express a derivative of, so u of, so certain values of a function u, so we have n plus 1 points altogether. So we'll find coefficients. So however many points we have, the same number of coefficients. So that some derivative of u at x naught is accurately approximated by this linear combination of these values of u. Okay. So we have n plus 1 points that may or may not be equally spaced, although most applications they will be, the x values. So what are the n plus 1 coefficients we can use to linearly combine these values so that no matter what u is, what we have is a decent approximation of whatever derivative of u we're seeking. So it could be first derivative, second derivative, whatever. Okay, so I showed you in a certain case where we had the second derivative, and I had m equal 2, so I had 3 points. So I had x naught, and then I had a point to the left and a point to the right, like plus or minus h. And I showed how you get those 3 coefficients in that case to get the center difference. But what do you do in general? Okay, so as in the example, we use a Taylor expansion. So I have u, the sum of, now this notation, something you need to get used to. Superscript in parentheses means derivative, so this is a jth derivative at x naught. Okay, so what I'm going to do is substitute that Taylor expansion in here, and I'm going to introduce shorthand here. That's that kind of thing. So you're going to let xi bar be equal to xi minus x naught. Just so otherwise you're going to have xi minus x naught all over the place. It's going to really clutter things up. Okay. So I'm going to substitute xi for x in the Taylor series. So you're going to have xi minus x naught, but that's just going to be xi bar. So now what you get is AI times Taylor series, so uj x naught over j factorial xi bar to the j. But now, as always seems to be useful in these situations, whenever you have a multiple summation like this, to change the order of summation. So we'll do summation over j outward. So you're going to have anything that doesn't depend on j, I'll move out here. So that's just a derivative, oops, I keep forgetting that, over j factorial, and then inside I have ai xi bar to the j. Okay. And this is supposed to approximate okay. I was giving myself these notational quandaries. I'm trying to approximate a certain derivative of u. I used j earlier, which was a bad idea because I have j over here. I'm going to pick a different letter. So kth derivative at x naught. So that's the derivative I want. So now, if I want to choose my AI, that's the only thing I have control over here. I want to choose these coefficients so that this is satisfied. Keep in mind that u could be whatever. I want to make sure that other derivatives of u end up going away. So in other words, I want this sum of ai xi bar to the j to be equal to 0 if j is not equal to k. So, in other words, if I can make this 0, then all other derivatives will not appear. I basically want to pick out what I want, like the kth derivative. So, it gives me my other condition. AI xi bar to the k, I want to be equal to k factorial. So if I can make this k factorial when j equals k, that will cancel with this k factorial. I'll get kth derivative, which is what I'm after. So I just need to choose my a's so that as much as possible they satisfy these conditions. Now I have m plus 1 unknowns, my a's. So to uniquely determine them, I should only have m plus 1 equations. So really, I only get to enforce this for j going from 0 to m. So that'll be my m plus 1 equations. So m of them will be this. In other words, skipping over j equals k. And then I have this one. So total of m plus 1 equations for m plus 1 unknowns. Questions so far? Now, as seen last time with the example, these are m plus 1 linear equations. Even though the coefficients are nonlinear functions of x, at least the unknowns are involved in a linear way. So if this is a system we can solve by Gaussian elimination or whatever. So the system equations we want to solve is VA is equal to B, where, so now I'll define all these things. A is just a vector of our unknown coefficients. B is a vector of all zeros except for one element that so entry k plus 1 has to be equal to k factorial. I say k plus 1 because we're numbering from 0, 1, 2, etc. And then the matrix V comes from all these powers of x.
It's like k plus 1 to the power.
What's it? K plus first.
Oh, k
Yeah.
plus.
Yeah, it's a ST.
K plus first.
Yes. Okay. Right. What?
K plus first.
Yes.
K plus first.
Yes. That. Okay.
Parentheses. That's why.
What?
I was trying to put like all like k plus. I don't know.
Okay.
I thought it was a power.
Well, I did write it that kind of font, so.
Got it.
Okay. Never expected that to be the hang up, but yeah, okay.
It's all really confusing.
Well, but again, I never expected to give a whole lecture on QR factorization, only to find that students couldn't tell my A's apart from my Q's. So, yeah. Teaching is always adventurous that day. It's, well, I guess, as all of you know by now. Okay, so what we have here, all the different xi bars raised to powers. So like A0, and since we have AI, hold on, let me make sure I get this right. Yes, okay. So, oh, I almost wrote down this matrix completely wrong. So, take a look at my notes. All right. So, if we try to fill in this matrix, say row by row, so values of I correspond to columns, because unknowns correspond to columns. Equations correspond to rows. So the first equation, k equals 0, I have all these xi bars raised to the 0 power, but that's going to be 1. So first row is going to be all ones. Now, for the second row, k is equal to 1, so I have all these to the first power. So you're going to have x0 bar, x1 bar up to xm bar. But keep in mind how I defined xi bar is equal to xi minus x0. So what's x0 bar?
X0 minus X0.
Yes, which is also known as, yes. Yeah, so this one is 0, but only this one. Okay. And then we just keep raising this to higher powers. So this will also be 0, so x1 bar squared, x2 bar squared, x squared. Okay, and we keep going down to x1 bar to the m, x2 bar to the m, down to xm bar to the m. Okay. All right. Now, so this matrix is called a Vandermonde matrix. Well, I think what I've written here is actually the transpose of how a Vandermonde matrix is defined. I don't remember, and I'm too brain dead to look it up. The point is, when you have a bunch of x values and fill in successive either rows in this case, or it could be columns, of raising them to first the 0 power, first power, second power, and you keep going. So anytime you have that, that's a Vandermonde matrix. And it is invertible, as this has been proven, invertible if all the x values are distinct. So as long as no two of these points repeat, you're good. Otherwise, two rows or two columns would be identical, and that always makes a matrix singular. Okay. So this system, it can be solved. So by choosing the same number of unknowns and equations, we can guarantee a unique solution. So in the example from last time, it really is a 3x3 system. And by having these ones up here, what we're saying is that if I multiply this matrix by this vector, and note the first elements on the right side is 0, I'm saying that a0 plus a1 plus a2 up to am must be 0. The sum of the coefficients must be 0. That was one of the equations from last time. The two of you who were here might recall. And then, because of these zeros here, the other two equations had only two terms in them. So that made it a lot easier to solve those equations. So in that case, we just had this relatively simple 3x3 system to solve for the center difference for the second derivative. And I gave you guys other solutions, like for a case where k is equal to 1 for the first derivative of the forward difference, backward difference, center difference. Okay. Now, so those, already covered those. Okay. All right. Now, so in general, if you set k equal to m, actually be careful about this. All right. In other words, the number of points, like if you use a minimum number of points needed to approximate that derivative, I'll say generally is order of h if you make all the points equally spaced. All right. So, in other words, if you try to approximate a certain order derivative, say if I want a third derivative, I need to use at least 4 equations to get any approximation at all. If that's the minimum that I use, and my points are equally spaced, I'm going to get first order accuracy. And I say generally because it's not always true. For example, last class was a counterexample. I had k equal to 2. I wanted a second derivative. And I used m equal to, therefore, 3 equations. Because there's n plus 1 unknowns, n plus 1 equations. And I actually got second order accuracy. And the reason for that is because of symmetry. So sometimes when your points that you're using have some symmetry to them, like in that case I had x naught in the middle and I used x naught minus h and x naught plus h, you can get some cancellation of errors that can lead to higher order accuracy. But generally this is what you, and if I use more equations, therefore more points to approximate my derivative, I can get higher order accuracy. So in other words, the minimum order of accuracy you can expect is h to the m minus k plus 1. So that's the order of accuracy you can expect, with the possibility of maybe getting one degree of accuracy greater if there's some nice symmetry to help you out. Okay. Any questions at this point? Because pretty much no class ever has any questions ever. I've come to conclude after all these years, but yeah, I think it doesn't hurt to ask. Okay. Now, the thing is, since what we have here are powers of x values, another way of looking at this is, I can think of a0 to am as polynomial coefficients. That, especially, it's easier to see if I look over here. This is a polynomial of x bar, where I've plugged in selected points, x1 bar, x2 bar, etc. So I want this polynomial to be equal to 0 for, wait a minute. I may have just said something incredibly stupid, hold on. I was hoping to tie this in a polynomial interpolation, but I think that tie in might fall flat. Actually, yeah, there's not a polynomial evaluation because I'm plugging in different points. Okay. Well, dang, that was disappointing. Okay. I mean, there is a close connection between approximating derivatives by finite differences and polynomial interpolation. I was hoping it's something I could make that tie in easily just from what I already have written on the board, but it doesn't seem to really be working out that way. Okay, so in the case if I had the actual van der Waals matrix and not its transpose like I have here. Well, dang. Okay, because really what I'm doing is, another way of looking at finite difference methods, and this is something I covered them in 46560, is that when you're trying to find these coefficients, the A's, another way of looking at how I come up with them is, you're approximating your function u by a polynomial that passes through u at these points. And then you're taking the exact derivative of that polynomial. And that's what gives you your coefficients. And it may well be that I'm just too brain dead to really present it in a more elegant way than I would like to, but I'll just do what I normally hate to do and just cut to the punchline. Okay, I shouldn't call it punchline because nobody laughs at this stuff ever. But, right. Because there's really two ways to come up with finite difference schemes. First way is what I've shown you using Taylor expansion. The other point of view is Lagrange interpolation, that the coefficients, so AI, is equal to, I need to consider the k factorial times the, actually, no, I don't want that in here. Is Lagrange polynomial of degree m. But you take the derivative, you take the, whatever derivative you want the k derivative, so you got to take the k derivative of this, evaluate it at x naught, where this is the ith Lagrange polynomial for the points x naught, x1, up to xm. And to refresh your memory, you've all seen Lagrange polynomials in one class or another, but for some of you it's 4 years ago, and I think for one of you it's been more closer to 4 days. So, okay, 6 days. The Lagrange polynomial, degree m, is defined by a product of x minus xi over x minus xj over xi minus xj, which ensures that Lagrange polynomial is equal to 0 if, okay, so if I plug in xj, I get 0 if j is not equal to I, this I, and 1, it does equal. So I can construct these Lagrange polynomials, take their derivatives, so take the derivative that I need, plug in x naught, which is the point at which I want the derivative, and bam, those are my weights. So I can get them that way instead of solving this system of equations. And that's actually more efficient. To solve a system of equations, so it's m plus 1 by m plus 1 system of equations, So let's see if anyone remembers their numerical linear algebra. If I have an n by n system of equations, that takes order n to the what operations to solve? Is it n to the first, squared, third, fourth?
I'm gonna go first.
I say squared.
Say the question again.
Okay, so like solving ax equals b, Gaussian elimination, that sort of thing, takes order n to the what operations to carry out?
Gal.
Yeah, okay, solving system by Gaussian elimination, LU decomposition, that sort of thing. Yes, gold star for you. Yeah. So yes, it's a cubic operation in a number of equations and unknowns that you have. That's terrible. We like to avoid that. Whereas constructing Lagrange polynomials, that can be done in order m squared operations. So we're saving yourself a lot of work doing it that way. Now, for most practical applications, m is pretty small anyway, but still. What if you want to use a lot of points, which actually spectral methods do? Okay. So that's one nice thing about this approach. And the way you can see that is from one of the first equations that I wrote down. Kth derivative at x naught, I want to approximate by a sum of these coefficients times u at xi. And the thing is, I can first approximate u by an interpolating polynomial. So I have u of xi, the same points I'm using to get the derivative, I included here, multiplying the Lagrange polynomials. And why does this work? If I plug in x equal xj in here, then I'm plugging in xj here. So when I is not equal to j, this becomes 0, drops out. When I equals j, I get 1, and I get u of xj. So that's my way of approximating u by a polynomial. But now, what I want is a kth derivative of u, at x naught. So what do I do? Here, I took the kth derivative, and I plugged in x naught. So now I do that on the right side also. U of xi is a constant. Leave it alone. I take the kth derivative of the Lagrange polynomial, plug in x naught. So now, if I match this to this, that's AI. Because these match, so what's left? There you go. So that's the easiest way to see that you can use Lagrange polynomials to come up with finite difference approximations. Lagrange polynomials have, polynomial interpolation in general has a nice error formula too, so that can be used to come up with the error in finite difference approximation, but I won't get into that now. Okay. Let's see, do I really want to bother with this? I guess I do if it's going to come up in the homework, but I'm not sure if it will. I'm going to check real quick. Well, definitely doesn't come up in the first one. Oh, the second one's in spectral methods. Okay. Well, I'll make a brief comment about this. And okay, half hour left. Okay, now because it comes up often enough in applications, PDEs are in a divergence form. So I'm going to look at two slightly different PDEs. Okay. So what we have here is both PDEs have some variable coefficient A of x. So we're assuming that A of x is not constant. If it was, we could pull it out of the outer differentiation, PDEs would be the same. But these are not exactly the same. So this PDE is written in what's called divergence form, where we have derivative of this whole expression in respect to x. So now this is one dimension. In general, like higher dimensions, you get something like this: divergence of coefficient times gradient of u. So the upside down triangle of the delta means different things. Here it means a gradient, and on the outside it means divergence. Now, if I were to write this out in terms of the definition of gradient and divergence, that means the same as a u x x, like what I have here, plus a u y y, and if this is 3D, a u z z. Just because that's what the divergence operator does. You have a vector valued function, but divergence takes partial respect to x of a first component, partial respect to y of the second component, partial respect to z of the third component, etc., and you add them all up. It's like a dot product, which is why the dot is there. Okay. Now, what I could do is I could expand this using the product rule. I can carry out the outer differentiation. That would give me a uxx plus axux is equal to f. So notice that the leading term of the PDE in that form is the same as in the other PDE, which is in non-divergence form. Okay. I should mention that everybody on the right side of the room either is dealing with or will deal with the non-divergence form of this operator. Because it's eigenvalues, eigenfunctions have nicer properties. Whereas my former student, Elise Garon, had done some work on the divergence form, which also has its advantages because of the symmetry of it. So I can make the symmetry more apparent if I write it differently. Partial respect to x, a of x, partial respect to x of u. So we have, if you look at the sequence of operations, you take u, differentiate it, multiply by a, then differentiate it again. So the sequence of operators is the same forwards and backwards. So that's what I mean by the symmetry. That the non-divergence form does not have. Okay. Now, so with this kind of Poisson-like equation, what I'd like to do is, like I did last time with Poisson's equation, discretize it using finite differences and come up with a system of linear equations to solve. So when I had this system from last time, or this PDE, I wound up with this system, AU is equal to F, where A is equal to over H squared, and I had 2, 2, 2, minus 1 above, minus 1 below. These are in the case of Dirichlet boundary conditions. So I had that nice matrix to work with. And one of the nice things about this matrix is it's symmetric, which we expect from second derivative, that is it's called a self-adjoint operator. So anytime you discretize it, you should expect to get a symmetric matrix. Although sometimes the boundary conditions might throw that off. Now, what happens when we have the coefficient a of x in the mix? I want to do the same thing. I have my PDE, I want to get a system of linear equations to solve using finite differences. What would that system of equations look like? Or what would the matrix look like? So what I'll do is I'll show some possibilities. Now, this matrix only applies if I have Dirichlet boundary conditions. Because we talked about last time how it can change if ever boundary conditions. So I'm going to stick with that assumption in this case, just for simplicity. Now, I'm going to define some notation here. I can define D plus to be this matrix where I have minus ones along the diagonal and then ones above. And that's it. Everything else is 0. Okay, so there's minus 1 to the left of this. This is for forward difference for first derivative. I mentioned that rule last time. Because, so for instance, u prime at x1 would be u of x2 minus u of x1 over h, forward difference. Now, also in backward difference. So here we have ones on the diagonal, minus ones below, and then zeros everywhere else. So that's the backward difference. Okay. These are both first order accurate, as I mentioned last time. And then D0, 1 over 2h. This matrix then has zeros on a diagonal, ones above, minus ones below. That is the centered difference. Also for UX. And I need to make a distinction because I'll let this matrix D2 is the matrix I have over there. It's a more appropriate name. Second derivative, center difference. Actually, yeah, it's the opposite sign of that one because that one's for minus UXX. Centered, difference for UXX. Okay. Second order accurate. Well, both center differences are second order accurate because the symmetry leads to cancellation of errors. And one more matrix I'll call A is a diagonal matrix. Because my coefficient is A of x, I'll evaluate the coefficient at my grid points. So when you're multiplying by a coefficient in like a differential operator, that's equivalent to multiplying by a diagonal matrix. So anytime you're doing point-wise multiplication, that's how you implement it like as a linear operator. Okay. Okay. So, given these matrices, how can I discretize either one of these PDEs into divergence form or non-divergence form? The discretizations of both PDEs to get a system of this form, LU is equal to F. Wherever vector F comes from the right side, U represents the solution, and L represents whatever differential operator is shown here on the left side of the PDE. So L is a matrix, so how do we get that matrix? So first I'll talk about the non-divergence form, because really there's not much leeway there. So L, the matrix L, would be a matrix A times the matrix D2. So the D2 covers the UXX part, and then the matrix A here handles the multiplying by A of X. form is more interesting. So if I take this divergence form, but I write it this way, so a uxx plus ax ux, I could write that as, let's see, L is equal to same thing for a first term, and then for the second term, well, I'll write it this way, is a prime, and then for second order accuracy, I want to keep second order accuracy, I use the center difference. So a prime is equal to a prime of x1. So you need a derivative of a to get this matrix, or at least you can approximate it somehow. Again, by a finite difference. And finally, if I had still kept the divergence form, AUX X, I could do this instead, where I have L is equal to forward difference times A times backward difference. So the D minus handles this differentiation with respect to X. Then I multiply by A. And then the outer differentiation is handled by D plus. Now, you might think, well, does it really matter which one we use for a divergence form? Because 2 and 3, options 2 and 3, those are of the same PDE. Number 1's a different PDE. But I want to point out that only this form of the 3 I've shown you is symmetric. So if you, it's not something that will be readily apparent, but if you were to actually work out the entries of all 3 of these and see what happens, like if you take the transpose, then you don't find symmetry in this one. In fact, one thing I forgot to mention earlier, this, and you can see by looking at the matrices though, the backward difference is equal to minus the transpose of the forward difference. So that contributes to the whole thing being symmetric. Now I didn't have to use backward here and forward here. I could have used forward difference for both, or backward difference for both. I could, but that would not give me symmetry. I also could have done forward difference here, backward difference here. That would be symmetric. Okay. Why do we want to? Why is it so important to? Why is it helpful, at least, to have symmetry? Why is it better to solve a symmetric system given the option?
It's just easier, symmetric, positive, definite.
So actually, if I were to negate this, this actually would be symmetric, positive, definite. So if I know that, what option do I have that I wouldn't have otherwise to solve it?
But it's some kind of factorization.
Yes, and at least 2 of you should know what?
QR.
Not that one.
Cholesky.
Cholesky, yes. I guess we can just run through until you get them. Yeah, Cholesky. What's the advantage of Cholesky over just plain old Gaussian elimination?
It's a better order convergence. Well, Gauss is into the third.
So is Cholesky. Okay. You don't remember, Billy? Guess? That's okay, it's a while ago. So. I might have brought it up in this class. I don't know if I did or not. Okay.
Nothing's coming.
Okay. Well, it's a very Monday-ish kind of Monday. So it's slightly more efficient. So Gauss elimination takes 2/3 n cubed operations, and Cholesky takes
1/3.
yes, yeah, it takes half as many. Well, gold star for you. Yes. So if it's symmetric but you don't know but it's positive definite, you can also do what's called the Ldlt factorization. That's for symmetric matrices in general. That also takes 1/3 n cubed. So yeah. So symmetry is nice for that reason. And symmetric matrices are also guaranteed to have real eigenvalues. This operator actually turns out both of these operators have real eigenvalues. But yeah. So I want to point out the importance of taking advantage of any symmetry or self-adjointness in your PDE that should be reflected in your system of equations that you use to find approximate solutions. So if you have symmetry or self-adjointness in the PDE, you ought to have symmetry in your system of linear equations. And there are many properties like that that PDEs have that it's important to be able to preserve if you can. Okay. Well, I think I said I was going to say a few words about this, and time kind of got away from me here. Then again, the other topic, well, I only have one topic left in this chapter, which I'm not going to attempt to cover in the last 7 minutes. It's not an easy one, so I think I'm going to make that wait, and maybe I'll be less brain dead on Wednesday. Okay, well, really, it's the only possibility left. Okay, so see what you can do, between now and Wednesday to take a look at some of the homework in case you want to have questions on Wednesday. So, because you keep asking every day, do you have any questions? And maybe one of these days there will be one. Yeah, hope springs eternal.